In the reply to the email or whatever, let's see what it says. Yeah, cool. In the reply to the announcement, I gave you guys, I thought, a pretty strong hint about problem one, so I just want to explain exactly what I meant by that really quickly. So let's look at that particular circuit. And I'm going to look at it kind of in a lazier way. So here's, actually, this would be VDD because it's MOSFET. You guys would catch what I was throwing either way. Here's some drain resistance RD. This RS down here is just the small signal resistance of that diode connected transistor. I'm just going to call it RS. This is our bias voltage. Here's V out. Here's R sig. And here's V in. My hint mainly talked about the output resistance because it behaves a little bit differently than you might expect. So let me explain explicitly what I mean by that by looking at the core of this amplifier, right? So if we were trying to find the output resistance of just what I have circled here in orange, it would look something like this, where we're treating this node right here as the input. So our gate would be grounded. Over here, we would have GM VGS. There's R naught. Our drain is actually not grounded. It's where we are going to apply our input signal. Yeah. No, or take our output out. So this is what our circuit would look like when we're taking the output resistance explicitly. That guy's going to look like a short circuit, and we're going to apply a test source over here. Let's just call it Vx, and this current is Ix. And by inspection right here, we could see that VGS is 0, and so the output resistance is just, actually, I forgot an RD here. Let me fix that really quickly. Our output resistance would just be R naught in parallel with RD, right? If we were just looking at the part that I circled in orange. If we were to include that resistance RS, it would go right here and it would be shorted out, okay? But the presence of that signal resistance, R sig, messes with stuff. And so let me explain explicitly what I mean by that. So we would have R sig right here in series with our input voltage source if we were looking for the small signal of this whole thing. When we short out that input voltage, because we're trying to find the output resistance of the network, VGS is no longer 0, which means the output resistance is no longer just going to be R naught in parallel with RD. And I'm saying VGS is no longer 0 because I can see very easily that the voltage drop across those two resistors in parallel is actually where VGS is. So the output resistance of this particular circuit looks the exact same as the output resistance of a common source amplifier with emitter to generation, which is what I mentioned in my email specifically. And this is why. The presence of this signal resistor right here effectively gets rid of the benefit of us shorting out everything that was connected between the source and ground when we short out that input voltage. So you need to take that into account in your output resistance calculations. And you could either analyze the circuit directly. It's not particularly difficult, or at least I don't think it is. But again, I'm a jackass who's done this a bunch. Or you could just refer back to your notes, because this is the exact same configuration as if we had just had common the output resistance of a common source amplifier with generation, right? So it is actually something that you've seen before. So that's how I would take care of problem one. The input resistance, the gain, and all of that kind of stuff should work normally. Now, a couple of you guys have been asking questions about problem three. So let's take a look at that guy really quickly. So problem three is something like this. Let's say this is V bias. I don't know. If this is transistor M3, let's call this 3. If this is transistor M2, let's call this V bias 2. Here's our input voltage. Here is our output voltage. And this circuit is just a fancy representation of this guy. So how I would start approaching this, and I think that it's exactly how I suggested earlier, is I'm just gonna figure out what the resistance of that bit that I just circled in red is, okay? So I'm gonna draw a small signal model for that. So let's start with the transistor M3. So this will be my gate for M3, and it's grounded. So I'm gonna call this G3. Here is VSG3. GM3, VSG3 in parallel with R03. This is my source of transistor 3, and it is at AC ground. This is my drain of transistor 3. Then down here below it, I'm going to have effectively an identical small signal model. Here's my gate of 2. GM2, VSG2, R02. This is my source of 2, my drain of 2. These two nodes are tied together. Here's where I'm applying my test source. So the first thing that we can observe is that VSG3 is just 0 volts because the source and the gate for that transistor are at AC ground, which means this guy is an open circuit, and so we just get an R03 from up there. Now I'm going to redraw this in a way that helps me think. So instead of drawing it with an PMOS transistor, I'm going to draw it like it was an NMOS transistor. So I'm literally just going to change a couple of things here really quickly, right? So here's my gate for transistor 2. I'm going to call this VGS2. This is my source for transistor 2. This is that resistance R03 that is between the source of 2 and AC ground. So it's taking the role of literally that whole thing right there. Here's GM2, VGS2 in parallel with R02. Here's my test source applied between the drain of 2 and ground, exactly like it was previously. So all of the connections are exactly the same. I just flipped the polarity of VSG to VGS, which allows me to change the direction of my current source, and voila, it's the exact same thing as an NMOS. Okay. So I wanted to find my resistance here. I'm going to call this current IX minus GM VSG2. And that should have a subscript 2 as well. Right? So that's just from doing Kirchhoff's current law. And if I write a Kirchhoff's voltage law equation, I could say that Vx is going to be equal to the voltage drop over resistor R02. So that'll be R02 times 1 minus GM2, VGS2. So that's the current, plus the voltage drop across R03, which is just R03 times IX. Oh, sorry. IX there. Yeah, IX minus GM to VGS2 plus R03 IX. Thank you for that. Yeah, I did. Going to come out to be a 1 in a minute when I do a simple substitution. So the substitution that I'm going to do is that VGS2 is just negative R03 IX. And I can say that because the negative polarity terminal is here. The positive polarity terminal of VGS2 is at ground. So this is just as good of a place to represent VGS2. So substituting that in, I get R02 times IX plus IX times GM R03 plus R03 times IX, and the output resistance, and I'm just going to call this R up. Let me explain what I mean by that. We went back to our original circuit diagram. That's the resistance that I see looking up. Or we could call it RS effective or whatever the hell we want to. But that's going to be Vx over Ix, or R02 times 1 plus GM R03 plus R03, which is R02 plus R03 plus GM2 R02 R03. I keep forgetting to put the 2 subscript on my transconductance. Sorry about that. But anyway. So that's my resistance looking up. Now we're just left with that circuit, which should be pretty straightforward and easy to analyze, because it's literally the exact same thing as this guy, which I believe I had you analyze in a previous homework assignment. Not quite sure why this was hard. Yep.
When we were trying to find GM, we having a lot of trouble knowing whether to use CLM.
So effectively, what I'm expecting you to do based on the information that you have is root to K ID.
Why are we not?
Couple of different ways to think about this. One, you weren't given enough information to figure that stuff out. Number two, channel length modulation isn't going to impact the large signal behavior of the circuit so much, but it's definitely going to impact the small signal. So that's a pretty traditional method used in industry, is we ignore channel length modulation in our large signal analysis and include it in our small signal analysis, specifically in integrated circuit design, where all of our resistors are relying on the small signal resistance of our MOSFETs.
We use lambda far enough.
Mm-hmm. Right, because we have no way to find VDS because I didn't give you enough information for it. Yeah. So I should have. In real life, you would actually do it like this. Like in industry, channel length modulation is neglected in the large signal analysis and only included in small signal. So it is introducing a little bit of error to our model, but it's also making our life significantly easier. Because we're not super concerned about what's going on large signal other than what the drain current is, because that's going to effectively define our operating point. So realistically, if we know what our drain current is, like we have the relationship, this is a relationship that you'll wind up using a whole heck of a lot if you happen to go into the IC design class in the fall. So we know that ID is equal to 1/2, let's just call it K because I don't care whether, well, actually, let's call it KN. Let's say that we're doing an NMOS. VGS minus VTHN squared, where channel length modulation is neglected, right? We could rearrange this and say that we would have twice ID over Kn is equal to VGS minus VTHN squared, so that the gate source voltage that we're having to apply to this thing is going to be the square root of twice ID over Kn plus VTHN. The reason why this relationship gets used so much in integrated circuit design, that's just mathematical manipulation there, is because in integrated circuits, we usually don't capacitively couple anything. Everything is DC coupled, so this is telling us what DC voltage we need to superimpose our AC signal on top of in order to make the device work the way that we want it to. So the drain current is the defining characteristic that tells us how every other parameter is going to come out. And that's typically what's done in IC. All right, so we've killed 25 minutes. Can we talk about the stuff I wanted to talk about today? Or Ryder, did you have another question? Are you sure? Yeah. Okay. I've got office hours this afternoon, just to be clear. Okay, so what I want to talk about now, and I almost decided to not do this, but we'll do it, is the Widlar current source. So the reason why I almost decided to not teach this is because it's not used a whole heck of a lot anymore. That being said, this Widlar current source is actually a part of the, why can't I never remember the damn name of this thing? The band gap reference circuit that I introduced earlier, and this is also actually the current source that's used to bias an op amp, like the 741 op amp that we very regularly use, okay? So the Widlar current source looks something like this. Here's our copy current. Let's call this guy over here Q1, this guy over here Q2. And the thing that makes it different than a traditional current mirror is that we include emitter degeneration on transistor Q2. Okay. Now, this is going to fundamentally change some things because we no longer have identical base emitter voltages for our sense transistor and our copy transistor, right? So this base emitter voltage here, VBE1, and this base emitter voltage here, VBE2, are no longer the same. So let's analyze this circuit and see what shakes out. So if I apply Kirchhoff's current law at this node, I can easily see that I reference is going to be effectively just the emitter current of Q1, right? So I'm going to have the base current and the collector current. I'm just going to lump those together. And so that's going to look like beta plus 1 over beta of the collector current of transistor 1. Are we okay with that? Nobody's saying they're not. So let me spell some things out here explicitly. So here's the current IC1. And now I'm questioning my notes. So the reason why I'm questioning my notes is because I definitely have this guy right here, an IB1, but I should also have this contribution right here, an IB2. And I don't know why I did not include that in my notes. So now I'm mildly scared. Yeah, let's see what happens. This could go terribly wrong. That's what I get for my hubris. Stop using these commas and all of this kind of stuff, right? So, like I said, this might wind up getting scrapped because the math might get real gross real fast. And I'll just sort it out later. Another reason to potentially drop it from the class. All right, so Over here, we're going to have beta plus 1 over beta times IS1 EXP of VBE1 over VT. And then over here, this is the part that I'm just adding on the fly. 1 over beta times, realistically, this should be ones in case these transistors aren't matched. This should be 2, IS2, EXP, VBE2 over VT. Let's let this sit here for a moment, okay? So that seems okay to me. Gavin, you got a question? Yeah. Yep, lumped in IB1 and IC1 to look like an emitter current. Absolutely. So our copy current is the collector current for Q2. So I can just say that that is IS2 times EXP of VBE2 over VT. And I'm going to rearrange this guy to say that VBE2 is VT times the natural log of I copy over IS2. This is going to get gross. All right, I'm about to do some logical hand waving away here because the math is going to get terrifying if I keep on this route. So let's think about a couple of things right here. Okay. So the base emitter voltage VBE1, will it be larger, smaller, or equal to VBE2? It will be larger, right? Okay. So that means the collector current for transistor 1 will be larger than the collector current for transistor 2. Which means the base current for transistor 1 will be larger than the base current for transistor 2. So let's say that the base current for transistor 2 is smaller enough that we can neglect this guy right here. And then this is going to make the math less gross. So yay for logic. Okay. What we're allowed to do now, I'll have to sit down and formally do this. I'm sorry. I was so cocky and arrogant earlier and I'm making myself look like a complete jackass, but you guys are used to that, so it is what it is. So rearranging this expression right here, lets us say that VBE1 is VT times the natural log of IREF over IS1 times beta over beta plus 1. I'm running out of room, so I'm going to put this underneath. And because of the properties of a natural logarithm, I could split this up into VT natural log with these brackets. IREF over IS1 plus natural log of beta over beta plus 1. So assuming beta is large, what's the natural log of something that's very close to 1? Something very close to 0. So we can throw that guy away. And we're left with VBE1 is approximately equal to VT natural log IREF over IS1. So if Q1 and Q2 are matched, IS1 will be equal to IS2, and we'll just call this IS. And so that allows us to say that VBE1 minus VBE2 is going to look like VT natural log IREF over IS minus VT natural log of I copy over IS, which will come out to be VT natural log of IREF over I copy. Right? So when I have the same thermal voltage multiplied by the difference in these natural logs, that's the same as dividing the natural logs. And because they're both fractions, division is the same as multiplying by the reciprocal, so the IS's cancel each other out. So using Kirchhoff's voltage law, I can also say that VBE1 minus VBE2 is just going to be, let me scroll back up here, the voltage drop across that resistor R, right? Which is just going to be the current flowing through the resistor RE times the resistor RE. What's the current flowing through the resistor RE? I copy times beta plus 1 over beta. Putting these two things together gives us beta plus 1 over beta times I copy RE is equal to VT natural log of IREF over I copied. And this is as far as the math can realistically take us here. So what a Widlar current source is used for is actually converting large currents, like you might get out of a DC power supply, down into very small currents that you can use to bias integrated circuits. Another advantage of the Widlar current source is it effectively makes the resistances required to do this significantly smaller than they would be just by using fixed value resistors, which makes it more appropriate for integrated circuit design. Let's look at the output resistance of this guy. So from a small signal perspective, our circuit is going to look something like this. So here's R01. GM1, VBE1, R pi 1, here's VBE1, and because this guy is diode connected, our base and our collector terminals are tied together like so. So here is the collector for 1, the base for 1, and the emitter for transistor 1. And then over here on the right-hand side, I'm going to have my second transistor. R pi 2, VBE2, GM2, VBE2, R naught 2. So this is the collector of 2, the base of 2, the emitter of 2. Between the emitter of 2 and ground, I should have a resistance RE. And then over here is where I apply my test source. Okay, so I'm going to put a dashed line here. What does everything to the left of this dashed line look like? A resistor. What resistance? So R naught 1 in parallel with R pi 1 in parallel with 1 over GM1. Okay? Which should be approximately just 1 over GM1 because those resistors will typically be larger. So now we can see effectively that we have this resistance R pi 2 in series with 1 over GM1. And since R pi 2 is likely much larger than 1 over GM1, we can almost treat that resistance like it doesn't matter. And we're going to effectively see a resistance of R pi 2 right here. If we wanted to get formal about it, it would be R pi 2 plus approximately 1 over GM1, right? So this voltage right here, negative, positive, VBE2. What does this look like? The output resistance of a common emitter amplifier with emitter degeneration. Something that we have literally already seen before. So our output resistance here is going to come out to be approximately R02 times 1 plus GM2 times RE in parallel with R pi 2 plus RE in parallel with R pi 2. So we have a very large, or at least larger than a conventional current mirror output resistance once again. Okay, so we've looked at the Wilson current mirror, we've looked at the Widlar current mirror. Those are kind of fancy ways of boosting the output resistance. Let's look at an easier way. And that easier way is, so I got my notes wildly out of order here. No, I didn't. I just forgot to bring the notes for a Cascode current source, but that's okay. We can just do it on the fly. All right, so Cascode current source. So earlier, we had talked about how a simple PNP or NPN transistor, when we apply some fixed bias voltage to the base, acts as a current source effectively, right? A constant value of VBE gives us some constant amount of collector current flowing through our device when we're not too worried about early effect on our DC analysis, okay? We've also observed that the output resistance of this thing is just R naught. Okay? For some applications, that might be okay. For other applications, we might need to boost that output resistance to make our transistor current source look more like an ideal current source. So one way to do that would be to utilize degeneration. Okay. So that's exactly what the Widlar current source does, by the way. We might have something like this instead. So this is RE. And this output resistance right here, I'm going to cheat a little bit here. Luckily, the output resistance of a degenerated thing is literally right above me. So I'm going to say that this is probably going to be R01, 1 plus GM1 times RE, where this is transistor, Q1. RE in parallel with R pi 1 plus RE in parallel with R pi 1. Now, there's a little bit of a problem with this, inasmuch as this physical resistor RE tends to eat up some of our headroom. What I mean by that specifically is that if we were concerned about the voltage here at this node for lack of a better word, let's just call it V out. The output voltage or the voltage seen at the collector of this degenerated transistor current source is going to be higher than the voltage seen at the collector of the non-degenerated current source. So in order to minimize some of that headroom loss, we can replace that resistor RE with a transistor, right? So when we have these two transistors stacked on top of each other, so let's call this one Q1 and this one Q2. V bias 1 and V bias 2. We should now see an output resistance of R01 times 1 plus GM1 R02 in parallel with R01 plus R02 in parallel with R01. Which output resistance do you think is going to be the largest? When you say the second one, you mean this one? I disagree. So the reason why I disagree is because R naught is usually going to be significantly larger than any resistor size we might choose to use for RE, because if we make RE too large, we're going to lose all of our headroom for any kind of amplification or anything that we're going to do by biasing with this, right? So if R naught 2 is much larger than RE usually, then the output resistance of this cascode configuration is going to be significantly larger than degenerating with a fixed resistance. So because I didn't bring my notes, and I don't have any math to particularly support this here, but I might upload and work that example or something like that. So typically speaking, the output resistance of just the transistor current source by itself, somewhere in the ballpark of 5 to 10 kiloohms, maybe up to 20 kiloohms, somewhere in that ballpark. So kiloohm size resistance. When we degenerate with a resistor, that's typically going to be somewhere in the ballpark of hundreds of kiloohms of resistance. Degenerating with a second transistor is actually going to put us in the mega ohm ballpark range. So pretty significant boost in input, or excuse me, output resistance. Just for nomenclature's sake, Q1 here is called our cascode transistor. And Q2 is our degeneration transistor. Could we make a cascode transistor, or excuse me, a cascode current source with a MOSFET? Absolutely. Is the equation for the output resistance going to be literally any different? I don't see an R pi anywhere in there, so no. Literally not at all. Exact same configuration, exact same. Now, so this is a true cascode. I want to be clear here. We have an NPN transistor on cascoded on top of another NPN transistor. We could do the exact same thing with a PNP transistor on top of another PNP transistor. Now, just for the sake of argument, let's look at a couple of configurations that would commonly be called false cascodes. So let's say that we had something like this. Here's Q1. Here's Q2, where one of them is an NMOS, or excuse me, an NPN, and one of them is a PNP. Why do you think this might be problematic? So let's look at Q2 right here, right? So this is our collector. It's at ground. This guy right here is our base. It's at a DC voltage, which at AC is going to look like ground. So what this guy up here, our cascode transistor, sees is a degeneration transistor that is effectively diode connected. And we know that a diode connected transistor exhibits a much smaller small signal resistance than a current source connected transistor. So by switching up transistor types here, so going from NPN to PNP or the other way around from PNP to NPN, is going to actually still going to give us some boost in output resistance. It's still going to work as a current source, but it's actually not going to give us even good enough output resistance to compare with just the generating by an actual resistor. So this is, typically speaking, avoided at practically all costs. It's just bad practice. All right, so not only can we cascode transistors together to make a current source, we can also cascode transistors together to make good amplifiers. Okay? So before we get into that specifically, I want to talk to you guys about a topic called short circuit transconductance. So we have defined transconductance to be a transistor's ability to generate an output current due to a small change in its input voltage. So for a BJT, we had the relationship, this is just the derivative of our collector current with respect to our base emitter voltage, which was just come out to be IC over VT. We derived that explicitly, if memory serves me correctly. And for a MOSFET, we would have the derivative of the drain current with respect to the gate source voltage. And the relationship that we've been using here recently is twice K ID. Well, this definition of transconductance can really be applied to literally any circuit where we expect to see some current at the output and we're changing a voltage somewhere. Okay? So let's say in general, that I have a linear circuit and I apply some input signal V in, I could define an output current I out to be flowing from ground into the device. And this is what I'm going to call my short circuit output current. And then I can define my short circuit transconductance, capital GM, to be the ratio of I out to V in under the constraint that the output voltage is 0, or we're short circuiting the output. So this short circuit transconductance just represents effectively a system's ability to convert a changing input signal into an output current, playing the exact same role as the transconductance for a transistor that we've been dealing with. But now, instead of looking at just the transistor's ability to do it, we're going to look at the system as a whole, because sometimes that's going to make the math less gross. So we can use this concept of short circuit transconductance to approach voltage gain from a slightly different perspective. Okay. So if we had a simple black box circuit, like so, where we had a very simple single-ended amplifier. So here are output terminals of our device. Here is our input signal. We can use Norton's theorem to effectively replace this two-terminal network with an equivalent circuit. So we could represent this thing as something like this. Where this output voltage V out is just negative I out times R out. And I chose to represent my current in that down direction as if it were leaving effectively our ground node, like we have up here. Since this current I out is GMVN, then our output voltage V out becomes negative GM R out times V in, and our voltage gain is just negative GM R out. Does this look maybe just a smidge familiar? Like, let's say that that capital G were a lowercase g. This is the exact gain equation for a common source or common emitter amplifier. But it turns out that it'll work for everything. Okay? So we've got 10 minutes left. So let's prove this quickly. So let's say that I have a common base amplifier. Here's RD. Here's VN. Here's V out. Here's VB. So let's solve for our voltage gain here using traditional methods. Okay. So our small signal circuit would look something like this. Here's RD. Here's our output voltage term, right? So let's run through this pretty quickly. Our output voltage here should be the voltage drop across the resistor RD. Oh, sorry, because this is a BJT, this should be RC. Sorry about that. Not trying to confuse you guys. So we could say pretty easily that V out is just going to be whatever this current is. Let's call it IC for lack of a better term. Times RC, right? Well, what's IC going to be? Applying Kirchhoff's current law, it's going to be the current flowing up through that dependent source, and it's going to be the current flowing up through the resistor R0, right? So that would look like negative GM VBE times RC plus VN minus V out divided by R naught times RC. We can see that VBE is just negative VN. And making that substitution is going to give us V out by itself plus V out times RC over R naught will be equal to positive GM RC times VN plus VN, times RC over R naught. My algebra look okay there? Factoring things out really quickly. We have V out over VN, which is going to be our voltage gain, is GM RC plus RC over R naught divided by 1 plus RC over R naught. And we could multiply through by R naught really quickly to give us GM R naught RC plus RC over R naught plus RC. There's our voltage gain. Again, we've done this a couple of different ways. This might look slightly different than how we've represented it previously, but it would give us the exact same numerical value if we plug things in, okay? So there's the old method. Now let's look at our second method, which is going to be using our short circuit transconductors, right? So let's find R out for this guy really quick, right? So to make my life slightly easier, and also because we're running out of time, I'm just going to make a copy of this. So if we were trying to find the output resistance of this thing, what would we do again? Short VN. Okay. All right, so with VN shorted, what's VBE? 0. So what's our output resistance? R naught in parallel with RC. Absolutely right. Great, that's easy enough. Now let's calculate our short circuit transconductance. So taking my circuit from above, my short circuit transconductance, I need to short out my output voltage node and find the current leaving ground from my live network. So what can we observe here really quickly? Is the resistance RC going to have any voltage drop or anything like that over it? Can't, shorted on both sides, right? So this guy right here contributes nothing. So that means I out is going to be this current plus this current. So I out is going to look like GM-VBE minus VN over R naught. What's VBE? Negative VN. So let's just replace that VBE with a VN and put a negative sign there. Capital GM is just I out divided by VN, which is negative GM minus 1 over R naught. So putting these two things together, our voltage gain for this circuit is, let me write it out here, sorry. Negative GM R out. So that's going to be negative times negative GM minus 1 over R naught times R naught in parallel with RC these negative signs cancel each other out. And so what I wind up getting is one over R naught plus GM times R naught times RC over R naught plus RC. Is going to look like RC divided by R naught plus RC plus GM R naught RC over R naught plus RC, which I'll be damned is the exact same thing. It'll work for any of our single transistor amplifiers very, very easily, but I would argue that using either method is roughly of equal difficulty. What we're going to see when we look at amplifiers that contain multiple transistors here in the next couple of days is that the short circuit transconductance method is going to make our lives much, much easier than trying to directly analyze cast-coded amplifier circuits. All right, so that's enough out of me for today, and we are caught up to exactly where I wanted to be. So all is well in the world. Yes. Yeah.
Would it be fair to try this method?
Absolutely. You want to? I don't know why you would. I mean, are you having trouble with the voltage gain?
Number one is.
I don't understand why one was an ASCII problem for voltage gain. Yeah, so let me draw it in a way that might help explain why that'll work, okay? So our circuit was something like this. Right? I'm just grounding that because I'm lazy. Okay. I'm going to call that node right there Vx. Okay. So the voltage gain of this circuit is supposed to be the ratio of V out to V in. Correct? That could be expressed as V out over Vx times Vx over Vn. Well, V out over Vx is just the voltage gain of that guy. And then Vn over or Vx over Vn is just treating this guy down at the bottom as a voltage divider because that's literally all it is. So if you wanted to do the short circuit transconductance, you could. Yeah, and by the way, this method right here is just depicting what I showed you guys how to do in 335, just in a slightly different way.